Welcome back to The Explainer. We're diving straight into Earth electrode and soil resistivity design, Part 1. You know, we spend a lot of time talking about high-level earthing philosophies, but today we're getting our hands dirty and looking at the actual physical reality of the ground beneath our feet.
Picture this. You take a copper rod and you drive it with the exact same amount of force into marshy ground, and then you try the exact same thing in solid rock. Guess what? You are going to get a resistance reading a literal 1,000 times higher in one than the other. So it's really not just about the metal you're burying, it's almost entirely about the ground itself.
Because let me tell you, soil resistivity varies wildly. I mean, it ranges from a highly conductive 200 to 350 ohm centimeters in a marsh, stretches through loam and clay at 400 to maybe 15,000, and then it just rockets all the way past 100,000 in solid rock. That is a massive difference, and it's exactly why your design calculations absolutely have to be based on site-specific resistivity.
Think of it kind of like pushing a drinking straw into wet sand. It's easy, right? Super low resistance. But try pushing that same straw into dry, compacted rock. Even if you use a longer straw, you're barely going to make a dent. So when you're dealing with poor, high-resistivity soil, you can't just rely on brute force. You can't just say, hey, let's use a longer rod. It actually requires a totally different engineering approach.
Okay, let's pause for a quick knowledge check to lock this in. Based on what we just talked about, do you remember the resistivity range for clay soil? It's 400 to 15,000 ohm centimeters. That is a massive, massive range. And the reason for that huge swing? Well, it depends almost entirely on the moisture content. A heavy rain or a long drought will completely change your readings, which again proves exactly why design calculations have to rely on site-specific testing, not just some textbook guess.
And this brings us to a really strict regulatory reality. Now, you might be wondering, why not just use a building's existing structural steel piles as an earth electrode? It's already deep in the ground, right? Well, because mixing dissimilar metals in the soil causes galvanic corrosion. Over time, they literally just silently eat away at each other. Because of that major risk, the PUB completely bans using structural steelwork as a main earth electrode. Instead, you've got to select materials that are highly resistant to corrosion in that specific soil. From both a conductivity and a corrosion standpoint, electrical purity copper is by far the most satisfactory choice. Actually, scratch that. It's not just satisfactory, it's the strictly required choice if you want these systems to last for decades. So, let's recap. Before this, you knew the 4 earthing methods. Now, you know how wildly soil resistivity ranges, and you know we're heavily restricted to using high-purity copper. Which leaves us with one really big, provocative question. Now that we know the soil varies so much, and we're restricted to copper, how do we mathematically size that rod to actually guarantee a safe resistance value? Well, we are going to break down the exact formula, complete with a worked example, in Part 2 of this explainer.